Welcome back to High Performance Computing Advanced Scientific Computing course. This is lecture 11, Deep Sequence Models and CFD Application. In this lecture, we will talk about the capability and application of the deep learning in the computational fluid dynamic and we can say in the fluid dynamic area. And we will discuss how we need to use the parallel computing and HPC to be able to run this application. This is outline for this course. This is lecture 11, and as it promised, this year the course is focused on the computational fluid dynamic. In the beginning, let's have a review of lecture 10. In lecture 10, we presented application of the OpenFOAM, which is open source software for computational fluid dynamic. We talk in detail and we presented a practical example. We use the ELIA system to run the example. And of course, it's part of your assignment to run a simulation of the OpenFOAM with different number of processor to see how the parallel computing could help to get the speed up. Of course, there are many different examples you will use on the application. We provided you a general batch file, and you can change the case of the simulation, and you will see with different processor how the speed up gets up. Also, you will be able to change some setup on the code and maybe about the meshes, and then you will see how you will see different computing time, and it's one of the great example of the high performance computing, since in the CFD the HPC play one of the main role. You will see how these HPC resources help us to deal with large problems. Then we don't have much to talk about the review since it was practical lecture, and it's also available in the recording, and you have access to take a review and use it for your assignment. This is outline for this lecture, lecture 11. First, we will focus on the turbulent flow in the fluid dynamic area and why we need to use the deep learning model in this area, which is a type of the prediction or forecasting, and it's applicable in a broad area. And you will see the capability of the deep learning and how it's connected to HPC resources. Then the second part of the course, we will present some practical example of this area from our recent research also. The resources are available, and maybe some of you will be interested for the final project or maybe for the master thesis to use this model and develop them. Also, the data resources also available to work with them. In the second part, we will talk in detail, and we will have the result of this deep learning model in the fluid dynamic area. Indeed, the first part will focus on the turbulent flow and its prediction in the fluid dynamic. In the previous lecture, we had talked about the turbulent flow and the available numerical solution for the turbulent flow in the fluid dynamic, which is three main categories. It's called RANS, LES, and DNS. Firstly, we should point to the computing for this method. The cheaper one, LES, provide much better result than the advanced, but it's expensive than the advanced. Is around 10 to 5 times, and the DNS is the expensive one, which is provide about exact solution for the fluid dynamic problem domain. However, there are some limits. Firstly, for some large and real scale of the problem, still we are far from to have enough computing to run the simulation. And another thing is validating the solution. Usually, we need experimental data to validate the solution. And since the experiment is so expensive, so when we run the simulation, the computation of flight dynamic, sometimes we don't have the experimental data to test and validate our solution. This is one of the another problem that's available in the CFD area. Recently, the deep learning, which is a type of the network in the machine learning, presented capability for prediction in the nonlinear and random phenomena in different areas. For example, one of the first application was for the language development and voice recognition, for example. And it has a capability to be used in the fluid dynamic area, especially the turbulent flow, which is a random and non-linear phenomenon. A recent study also, they applied deep learning with a different setup. Some of them data-driven, some of them use the physics-based model to deal with some turbulent flow problem, and of course is related to compressible and non-compressible flow, which is this achievement it's showing us there is a possibility to use deep learning in the fluid dynamic area, and since we used it in the recent year also, we can say it's adding another approach in the fluid dynamic method, since we have the analytical method, we have the experiment, we have the computation, but it seems the deep learning will be another method which it's sit next to the computation fluid dynamic. One of the most capable method is from the recurrent neural network, RNNs. In this approach, we can we can use it for the sequential data, such as time series, and these match on some concept in the fluid dynamic area, because in the fluid dynamic area mostly we're solving the data on the time series, and we have two different framework used in the fluid dynamic, Lagrangian framework and Eulerian framework. In the Lagrangian framework, indeed the data it's behave like time series, and is the location and the time are related, and also the another properties like the velocity is function of the time. So it's presenting time series behavior. On the other hand, when we look on the turbulent flow, there are two categorized fundamental in the turbulent flow, which is called large eddy and small eddies. They are related to the structure of the coherent in the turbulent flow. Based off the latest hypothesis, There is a theoretical understanding for the small eddies, but there is not for the large eddies. One of the lessons learned about the large eddies, it seems they behaving with the memory of the time and of the location. They don't have properties locally, and they get effective from the other location of the domain of the problem. So this is helping us to say that the deep learning, such as RNNs, could be applicable in this area. About the structure of the deep learning model, of course, there are many resources, and in the HPC course also, lecture 7 is presented introduction to the deep learning, and you can see some example. You have access to the recording lecture. Um, uh, However, in this example from this lecture, since we are focusing on the sequential data, so we will talk about the RNN variants. Also, there are other applications use the convolutional neural network CNN for the study of the fluid dynamic. However, they have advantage and disadvantage, which from the recurrent neural network, because of the long short-term memory model, LSTM, it's able to make a simulation for the long term of the time series. It seems is more applicable for the turbulent flow. Here it's the short description about the long short-term memory model, LSTM. Here you can see its architecture, how it's created from the hidden state, and the new hidden state. Also, it has a memory cell internal state, and the forget gate and the input gate and output gate, making this structure able to deal with the vanishing gradient, which is available in the RNN network, and we can use it for the longer period of the time series data. This network developed and suggested in 1995. LSTM applies a gating structure to control the transient of the recurrent connector and can deal with the vanishing gradient issue. Recently, LSTM also applied in many studies, which is model time series prediction, which the longer period of the data. And there are some examples here which use in the fluid dynamic area, and some of them for the uh, use like the mixed model or hybrid model with the CNN and LSTM. Also autoencoder and LSTM, and they present successful results. From the LSTM model, there is another variant. It's called gated recurrent unit, GRU. It's working same to LSTM, but it has a simpler structure because the forget gate and input gate replaced with only one update gate. And from the literature and some applications, they reported that it can work with fewer parameters than LSTM, and the training rate is faster because the structure is simpler, and it seems could be provide the results same to LSTM. However, we used this model in our study recently, and regarding this statement, we can say it has the same result to the LSTM, and it's capable to provide prediction with the high accuracy. Uh, and then from the recurrent neural network, LSTM, one of the options that we can use it for the long period of the data time series, and the GRU variant, it's able to reduce the speed up maybe and provide same result with the LSTM. If we want to summarize the capability of the LSTM variance, we can say it's dealing with vanishing gradient and resolve it. The computation cost also could be reduced by some hyperparameter optimization. The parallel computation is essential in the deep learning, like the LSTM. From the literature also, GRU can perform faster with fewer data and results sent through the LSTM. And here there is a presentation from these two different cells and how they processing the data. Regarding the comparison of these two models, we applied them for the data from the turbulence flow. In the recent work, we used for 80% training, and the comparison between GRU and LSTM show the GRU has between 8 to 12% faster than LSTM. And with 60% training, 5 to 10% faster. With application of GPUs, when come to the HPC, the LSTM score has the same speed up from our test. However, we cannot say this result could be universal because our data was not too large, and the period of the time series also was only around half of a second. But the prediction was successful for turbulent flow. So when we look at the capability of the LSTM and GRU, we need to think how we can use this capability for the fluid dynamic and especially turbulent flow. How we can design data which will be sequential in the fluid dynamic, and also we are thinking about it how we can have raw data, because in the most recent studies we need to do purposing on the data to extract some feature, some hidden feature, and then use the data for the deep learning or some reduced model, reduce order model to make the data applicable in the deep learning. But here we were thinking how we can have the data without any purposing, and also how the raw data could be able to determine the flow feature. There were some questions to be answered to design the data set to be matched as a time series and sequential, and then use them for the deep learning model. Regarding the capability of the machine learning for direct area, there are many studies and suggestions. One of the important review from 2020, it presented the machine learning for fluid mechanics and its capability, which suggested to use it. In our case, we focus on the turbulent flow, which is one of the unsolved problems in the fluid dynamic. It has a random and nonlinear behavior. It has a high dimensionality, and it's one of the major challenges in the recent century, the physics. The aim is to have a model of the deep learning for the turbulent flow, which not only solve a flow case, we want to have a more general and universal model. And also we can study the flow features. To be able follow these goals and this approach, firstly, the data from the fluid dynamic is a challenge. Here in this slide, you can see this presentation of the solution of the RANs, LES, and DNS for a jet. with different detail, which presenting the different capability of them. As we said, in the fluid dynamic area, for the laminar flow, we can say it's solved and we are good on this area. However, the turbulent flow, we are not able to solve every problem. And we talk in detail about the available computational approach. And here you can see the example from the solution. Uh, the turbulent flow behaving randomly, and about the theoretical understanding about it, there are some assumption and limit, and make the hypothesis be applicable on the specific area. Now let's think about the idea how we can utilizing the deep learning LSTM model of GRU for the turbulent flow. First, in this slide, you see these few figures. The first one in the left-hand side, it's presenting how the energy transfer from the large scale to a small scale. This shape you see here, when they are large, it's called large scale or large eddies, and when it's small, it's called small eddy or small scale. And based off the hypothesis, it say they are transferring from large to a small scale, they're transferring the energy. And it started from the Richardson in 1922, which suggested this idea. Then there is a hypothesis from Kolmogorov, which came from 1941, and it's corrected also again in 1962. However, it's called K41. Its hypothesis has some assumption. In the beginning, when this hypothesis came, it was imagination. Maybe this hypothesis could cover all range of the turbulent flow. However, shortly after some investigation, it's uncovered the some limit of these hypotheses. Indeed, in the Kolmogorov assumption, there are two main concepts. It's called homogeneous and isotropic, or which is required to the scale or the coherent has a homogeneous and isotropic properties. These two condition only available for the small scale, and we cannot see them for the large scale. Then a Kolmogorov hypothesis only cover the understanding regarding the small scale. And that's why in the some approaches in the CFD we can use this concept regarding the scale of the Kolmogorov and solving the problem. But regarding the large scale, still there is not a theoretical understanding, and therefore it's required to find more aid and help from approaches like deep learning, maybe be able to understand this phenomena from its structure. But how we can apply the deep learning? As we said, deep learning here from the sequential model, the LSTM, it's working with sequential data. From the lesson learned in the turbulent flow, for the large scale, there is a two main important lesson. Firstly, the turbulent flow can provide much more of the size than it's described on the hypothesis for the viscous flow, which is related to a small scale. And also, the each point in the turbulent flow has effectiveness from another point from domain of the problem. It means its properties are not locally, not in the time, not in the location, which it's important because when we use the deep learning and we're training the model with time series, that means we're training, for example, the previous time period, and we're expecting to see its impact or effect on the next period. This is something that could be applicable in the turbulent flow with the deep learning application. So here we get into the unsolved problem. One of the idea currently using the theory, experiment, and simulation. As you can see here, this quote from these two famous scientists. Kolmogorov hypothesis only cover a small eddies of the turbulent flow, and we can say the viscosity flow. And at the same century, Feynman said that turbulence is the most important unsolved problem of classical physics, and still it's unsolved. And there are many research ongoing on it. For example, because the most of the majority of the flow is the turbulence, so in many areas in the industry or in natural condition, we are dealing with turbulent flow. And to understand it and to solve some problem and to design some industrial element, it's required to know its fundamental and theory of these phenomena. Uh, so far, still many research ongoing. However, there are some other challenges. For example, the theory of the Kolmogorov, it's covering the area that the flow should be equilibrium. However, it seems there are some challenges that this equilibrium is not always available in the turbulent flow, and there is recently some other research available also from the Kolmogorov hypothesis. There are some power law available regarding the Reynolds number, and some recent research, which one of them last year, 2023, published. It show in some studies these hypothesis does not prove. So we can say, because we are using the hypothesis that so far does not proved on the experiment, deep learning could be great solution, which is only use the properties of the flow, and it doesn't use only any theoretical understanding or hypothesis in all its solution. Therefore, its application it will be great to deal with turbulent flow. To apply the deep learning, we need to create a framework or use the available framework. One of the great framework which match with the LSTM, the sequential models, it's the Lagrangian framework. In the Lagrangian framework, if we want to say simple description for it, we are following a particle in the flow. If we seed the flow with a particle, and the particle has the same density to the flow, when we follow the particle, we can see the move of the fluid flow, and then we can use these properties. For example, for every single time this particle has a specific location and a specific velocity, and the velocity and the location, both of them function of the time. Then, based of the time series, we have simply two function, which is location and velocity. The other point is regarding the data could be used in the LSTM or group. One of the main concept for the turbulent flow, which is a three-dimensional phenomenon. That means if we use data from the 2D model or 2D simulation, or we don't cover all the features of the flow, then it's required to have data from the 3D simulation to have actual feature of the turbulent flow. Then one of the great option to use data for the LSTM in the turbulent flow, it's experimental data. How creating experimental and obtaining the experimental data, it's so difficult, and we will see in the second part of this lecture how we try to make this model possible and run it with the LSTM. Regarding the turbulent flow, as we discussed before also, majority of the flow is turbulent, and here is the example. The first two figures you see in the left hand side presenting in the great application of the large scale. You can see here is the one of the solar flare happening here, and you see the scale of the solar flare. Next to it you see uh, the size of the earth next to this scale, and you see how this coherent is large and how it's different size with the earth. So we call them large coherent, large scale, or large eddies, and there is not theoretical understanding from these phenomena. And also you see another example from the turbulent flow surrounding aircraft, and also when the flow passing the object. There is an example of them, the Leonardo da Vinci, which is presenting the different scale of the turbulent flow. So we can say, as you can see, this is the broad application from the nature and from the industrial application. So understanding it and maybe using uh, a new approach, a novel approach to help to understand these phenomena, it will be great. We should point that using the deep learning need to have access to HPC resources. Without HPC resources, we are not able to run the large data or extensive data because it's costly in the computing. Here we finish the part 1 of the lecture 11. Here is the example from the neural network application for the liquid, and I suggest you watch the video. The link is available on the references of this lecture, and it's presenting how using the neural network could model and predict the liquid move with a different condition. In the second part, we will continue this lecture, and we will have some practical example of the deep learning for turbulent flow. So we will continue in the part 2. Thank you.